Hello student, today I am going to discuss about Lentz law and how Lentz law gives the direction of the induced current or EMF produced in the coil, okay, or in a closed circuit. And also we will discuss about that Lentz law does not violate the law of conservation of energy. And in next I will discuss about Fleming right hand rule or dynamo rule, and at last I will discuss how we can vary the magnetic flux by changing different parameters. Okay, so first, what is Lentz law? Basically, induced EMF, direction of the induced EMF or current in such a way that it opposes the cause of it. This is called Lentz law. Okay, this is the statements of Lentz law. Now, see in this figure A and figure B. In this figure, we have considered a coil. Okay, we have considered a coil. Okay, and we have we have one bar magnet. Now, when we move this bar magnet towards the coil, okay, now we know that through this coil one induced current will produce. The direction of the current is such that which opposes the movement of this bar magnet here. So north pole facing this coil, okay, front face of this coil. So when we move this bar magnet along this direction, here a north pole will produce. It means current will follow anti-clockwise direction, such that in this phase north pole will develop, so that north pole repel to each other. So it oppose the movement of this bar magnet towards this coil. Okay. Similarly, when we move away from the bar magnet from this coil, okay, so current induced direction of the induced current in such that it will be along clockwise, so that this phase act as a south pole. So we know south pole and north pole attract to each other. So when bar magnet is moving along this direction, it opposes the movement of this bar magnet. Direction of the induced current such that it opposes the movement of this bar magnet. Why? Because the direction, as the direction of the current is clockwise direction, so this front face act as a south pole. Now south pole and north pole attract each other, so it opposes the movement of this bar magnet along this direction. Okay, so now combinedly, if we use the Faraday and this Lentz law, from Faraday law we know in magnitude of the induced EMF is d phi dt, and if we combine the Lentz law by using Faraday law, we only find the magnitude of the induced EMF, but it does not give the direction of the induced EMF. By using the Lentz law, we can find the direction of the induced EMF or current. So combinedly, by using Faraday's laws and Lentz law, we can write E equal to minus d phi dt. Okay, so this is the combination this is the equation of combination of Faraday's law and Lentz law. By using this equation, we can find the magnitude of the induced EMF as well as the direction of the induced EMF. Okay. Now we have to discuss about that Lentz law does obey the law of conservation of energy. So Lentz law does not violate the law of conservation of energy. Okay. We know from the law of conservation of energy does not created or destroyed. It can be converted into one form to another form. So here, see again in this figure. Now, when we are moving this bar magnet, okay, along this direction towards the this closed coil. Okay, so according to Lenz's law, the north pole is developed here, front face and back face south pole. Now north pole repel to each other. So to moving this bar magnet along this direction towards the coil, we have to do, external agency have to do some work done, and this work done is converted into electrical energy. Okay, because north pole is repelled to each other, so we have, against this repulsive force, external agency have to do work to bring this bar magnet towards this coil. So that work done by the external agency is converted to electrical energy. Okay, so here work done, mechanical energy is converted to electrical energy. Okay, now you see in figure B also, when bar magnet is moving away from this coil. Okay, now what happened here, due to Lenz's law, this face acts as a south pole. So now south pole, north pole attract to each other. So because of this attractive force, we have to, external agency have to do work done to movement this bar magnet away from this coil. So this work done converted into electrical energy here also in figure B also. So here mechanical work done is converted to electrical energy. It means here energy does not create or not destroy, but here mechanical energy is converted to electrical energy. Okay, so Lenz's law does not violate the law of conservation of energy. Now next, we have to find the direction of the induced EMF or current, we have to use the Fleming right hand rule, or it is also called dynamo rule. Now according to to find the direction of the induced EMF or current, we have to always use Fleming right hand rule. Now according to Fleming right hand rule, if we stretch these three fingers, index fingers, central finger and thumb finger, such that it's perpendicular to each other. Now if index finger gives the direction of the magnetic field, thumbs gives the direction of the movement of the conductor, then this central finger gives the direction of induced current or induced EMF. And this rule is called dynamo rule or Fleming right hand rule to find the direction of induced EMF or current. Okay. Now we know this formula. The magnetic flux equal to vector B dot vector A equal to BA cos theta. Now how from Faraday's law we know that whenever magnetic fluxes is changed, then only induced EMF or current will produce. Now how many ways we can produce the change of magnetic flux? There are three ways. One is called by, see this formula, you have to memorize this formula, and from this formula, if how we can change phi means magnetic flux. If A and this theta is fixed, then by varying B only, magnetic field strength. So by varying B, we can vary the magnetic flux. So this is one process. Okay, here also we are doing these things in figure A and figure B. By varying the magnetic flux, we can produce the induced EMF or current. Okay, now number two, by changing the area A. Here if B magnetic field strength and theta is fixed, by changing B only, by changing A only, this area, okay, we can vary the magnetic flux. Okay, now number three is by changing angle theta. If magnetic field strength B and area A of the conductor is fixed, by varying the angle theta between direction of the magnetic field and direction of the area vector. Okay, by varying that angle, we can vary the magnetic flux also. So in this way, three ways we can vary the magnetic flux. Okay, so one by one I will discuss. Already discuss these things by varying magnetic field strength B. Now I will discuss these things by by changing the area of the conductor. Okay,